Okay, so introduction to probability distributions. Okay, so here's the probability distribution of a sum on two dice. The variable we're looking at here is the sum on two dice, and whenever we have a probability distribution, we have a list of all the possible outcomes with its related probabilities. So, and there is the definition of a random variable. A random variable is a variable whose value is determined by the outcome of an experiment. So, in this case, our experiment is rolling two die and taking note of the sum on the two die, and our random variable in this case is the sum on two die. Now, a probability distribution can either be in tabular form or it can be in graphical form. This I don't see very often, but it does occur. So notice here's the sum on two die across the horizontal axis and the related probability here. So notice it takes on an interesting shape. Notice the values are discrete. It's only the sum can equal 2, nothing else. The sum can equal 3, nothing in between the 2 and the 3, right? It's not continuous. We're looking at discrete probability distributions in this unit. To construct this probability model, it was necessary to assign a numerical value to each outcome, right? So there's the numerical value to each outcome, 2 to 12. This assignment of a numerical value to real-life occurrence is called a random variable and is usually denoted by x. In example 1, the random variable x was the sum of the two die, right? So the only difference between this unit and the last unit is that instead of looking at, well, what's the probability of a sum of 6, we look at the entire experiment. Okay, so we want to list all the outcomes with all the related probabilities. Okay. Define the appropriate random variables for the following experiments and indicate the values that the random variables may take. Okay, so let's look at A. A task force committee is to be selected, and it is important that there is a fair representation of males on the committee. Okay. So since we're focusing on a fair representation of males on the committee, our random variable x, the random variable x, is the number of males on the committee. What values can it take on? Well, values it can take on are starting with 0, 1, 2, 3. Notice these values are discrete, right? It's either 3 males. You can't have 3.145 males. It's 3 males. 3 dice are rolled, and the sum of the 3 dice is used to move a piece in the game. Part B. Well, the random variable x is the sum on 3 dice. The values it could take on are, I guess the lowest sum on 3 dice is 3, then 4, 5, and the maximum is the sum on 3 dice, which is the maximum value on any one die is 6, so 6 plus 6 plus 6 is 18. All random variables that we see in this chapter deal with outcomes that can be assigned values such as 0, 1, 2, 3. Random variables of this nature are called discrete random variables. Associated with each random variable, of course, is a probability. So when we know all the values with the related probabilities, that is what a probability distribution is. I'm going to ignore this example. I don't see. I'm not sure how helpful it is. Okay. So can I explain anything better? Okay. The expected value, that's another way of what the average value. Is simply the sum of your random variable x times its related probability. The quantity expected value x is also referred to as expectation. So let's take a look at this. Let's do a couple of examples. A game is defined by the rules that 2 dice are rolled and the player, there's a little p missing there, wins varying amounts depending on the sum of the 2 dice according to the following tables. Now, a sum of 7, he'll win $5, but you can win a $6 when you have a sum of 6 or 8. You can win $7 when you have a sum of 5 or 9. So when we ask the question, what can the player expect to win, we have to go by our random variable x will be the winnings associated with each roll. So the random variable x is the winnings associated with each roll. Okay, so our winnings go 5, 6, 7, 8, 9, 10, 5, 6, 7. So our winnings x are going to be 5, 6, 7, 8, 9, 10. Now, a sum of 7 must occur to win $5. A sum of 6 or 8 has to occur to win $6. Sum of 5 or 9 has to occur to win $7. Sum of 4 or 10 has to occur for $8. Sum of 3 or 11, so we have to calculate the probability of each of the sums, right? Of each of the winnings, sorry. And this is $2 or $12. So maybe we should do a little die chart here, because we need the probability of x. Then we'll have another column xpx. Okay, so let's do a little die chart here. 1, 2, 3, 4, 5. Oh, I forgot the 6. So sum of 7 is 1 right there, right? And so the probability of winning $5, maybe we should put dollar signs there, is going to be 1, 2, 3, 4, 5, 6, 6 out of 36. Now a 6 or an 8 is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 10 out of 36. Five or a 9 to win our $7 is going to be 1, 2, 3, 4, 5, 6, 7, 8 out of 36. 4 or 10 is 1, 2, 3, 4, 5, 6, 6 out of 36. $9, 3 or 11, 1, 2, 3, 4, 4 out of 36, and the last one's 2 out of 36. So XPX is going to be, well, what do you think this adds up to? Yeah, 36 over 36, which is 1. So now we can calculate our expected win. 5 times 6 over 36 is 30 over 36. 6 times 10 over 36 is 60 over 36. 7 times 8 over 36 is 56 over 36. It's kind of like a weighted average because we're calculating expected win. 48 over 36, and this is going to be 9 times 4, 36 over 36. 10 times 2 is 20 over 36. 36 over 36 for $9. And 10 times 2 is 20 over 30. So the sum of XPX is equal to 250 over 36, which is equal to 6.94. So the expected win or expected value of X is 6.94 cents. You can expect to win now. The cost to play the game is $7.50. So when they ask, is this a fair value to play the game? B, no. If you pay $7.50, you expect to lose 56 cents per game. Not fair. It has to be fair to both the player and the organizer of the game. So, for a game to be fair, the cost to play must equal the expected win. For a game to be fair, the cost to play must equal the expected win. Good? Okay, let's do a committee of 4 people. When we're choosing committees, order is not important. Committee of 4 people is to be chosen randomly from 4 males and 6 females. What is the expected number of females on the committee? So let the random variable x be the number of females on the committee. So there's our x. Well, what values can x take on? Sorry? 0 to 4, right? So we can now calculate the probability of x. So we have 6 females to choose from and 4 males. So we could go 6 choose 0. Out of the 4 males, we'll choose all 4. Divided by 10 choose 0. 10 choose 4, sorry. And that equals 1 over 210. Then we'll do xpx here. Okay, here we'll go 6 choose 1. 4 choose 3. 10 choose 4. And that equals 24 over 210. Six 2, 4 2, 10 4, and that's 90. It's just like the last unit, right? 3 of 6 females, we need 1 more male, divided by the total number in our sample space. Then here we have 4 females, 0 males, number in our sample space. So the sum of all the probabilities should add up to 25. It should add up to 1. Does it? Okay. And now we'll do xpx, and we will be able to calculate on average how many females can we expect to have on a committee. So this is 0. 1 times 24 over 210 is 24 over 210. 2 times 90 is 180 over 210. 3 times 80, 240 over 210. 4 times 15 is 60 over 210. The sum of xpx is equal to 504 over 210, which is 2.4. Just crunching out the numbers, right? On average, we can expect 2.4 females on the committee. So there's no such thing as 2.4 females. However, this is an average value, so here it's okay. The odds of being... Why do you say the probability? You're assuming what? Okay. Here, I'll just sign off and then I'll think about your question, which oh, here.